This is my following object lab for PHYS 2211. To start, what is our goal with this lab here? It is to compare theoretical models of free fall with and without drag to a real-world observation of a falling object. What are our models and physical principles? They include position versus time graphs, Newton's second law of motion, Newton's law of universal gravitation, and the drag force. What will happen? As a brief preview, although the computational model with only gravity deviates a lot from reality, the model with both gravity and drag closely models it to an almost uncanny extent. What are our main ideas for physics here? Following Newton's second law is the velocity update formula, which says that Vf equals Vi plus F divided by m times delta t. Similarly, the position update formula is Rf equals Ri plus V delta t. Drag force can be calculated using F drag equals negative BV squared times V hat, which is called the turbulent drag formula. Newton's law of universal gravitation states that F equals G times m1, m2 divided by r squared, but this can be simplified to just becoming F equals mg for objects near Earth's surface, which we are looking at here, where g equals negative 9.8 meters per second squared. Our experiment details. Basically, position versus time graphs are chosen because they're very readable and easy to understand. Velocity and position update formulas are chosen because we know what F net and delta t are equal in this case, and drag is used in order to better understand and simulate reality of free fall objects, which they have drag in the real world, so might as well try to model that. We assume that the mass of the object is 1 kilogram because all objects in a vacuum don't matter what mass they are. They follow the same speed no matter what, so it doesn't matter what mass we choose here. I chose 1. System is the whiteboard, and also the surroundings is everything else, like my hand or the air or the ground. The conditions are that the whiteboard is held 1.018 meters above the ground, and it's dropped until it hits the floor without any force exerted on it besides gravity. And all else is held constant. So yeah, and after the whiteboard starts falling, a group member, which is me in this case, records movement until it falls down on the floor and hits it. For our coding implementation, we use GlowScript to predict the position at each time, with gravity as the only force here. So we have a very steep curve for gravity, and it falls below 0 meters for the position at the y dimension, and has one force, which is gravity here, and here's the code for how it actually was made. And now for part 2 of our coding implementation, we use the exact same idea here, but with gravity and drag forces accounted for this time, so it's more realistic and complex. It has two forces up and down. Those are gravity and drag, respectively. The graph is more level now, it's more gentle and realistic, and it hits 0 when time ends at 0.6 seconds. And here's the code, very similar with more formulas here and there to account for drag. What are the differences? Basically, the predicted graph with only gravity shows how it's a much faster rate than everything else. Therefore, it's sort of the outlier and sort of the black sheep in this case. Meanwhile, the graph with gravity and drag, which is the yellow one, is almost the same thing as the observed graph, showing its viability as a predictor of motion. It's a very good model in this case. For potential errors, the video wasn't calibrated that well in the tracker app, as the position when t equals 0.3 seconds is somehow just not there. So the graph is simplified in the range that's right before and after 0.3 seconds, and therefore it's a little bit jank there, I won't lie. Proportionality, constant for drag, is also a little bit inaccurate because I plugged and chugged to find a value that would make position y equals 0 when t equals 0.6 seconds. So therefore it could have been wildly different or even like way off. In that case, if b was way off, then the computational model wouldn't have been accurate at all, and I would have had a very naive, I guess, model that I use in this lab. So yeah, I would need to know what B is to actually predict the real motion if I had to do it. And now for what if and what does it mean questions. Which models predict terminal velocity, if any of them? The second one does only because it predicts that when the graph levels off towards the end, it's more flat. So the velocity is therefore constant. In that case, it means that F net is 0 because gravity equals the drag force, and therefore there's no acceleration or change in velocity at all. Therefore, that's when the terminal velocity, which is negative 2.3 meters per second, occurs. The first one does not have any prediction because it is only gravity but not actual drag force involved in the first model. Therefore, you can't use it to predict terminal velocity. And what if the object was initially thrown downward instead of being dropped from rest? Well, in that case, it still would have the exact same velocity at the end because it reaches back up and it climbs back up to negative 2.3 meters per second no matter where it starts off. So no matter where you started with, it has the exact same terminal velocity at the end despite having thrown downwards or being dropped from rest. It does not matter. For conclusion here, basically, computer models that account for both force due to gravity and drag are very accurate predictors of an object's motion in free fall. In our formula, drag depends on the square of the speed rather than being linear because it makes more sense and portrays more closely real world phenomena as opposed to more lecture based theoretical videos. Whenever you see classical problems and you solve them with 2D kinematics, it's almost never accurate because an entire force called drag is not accounted for with those sorts of problems. And therefore, theoretical physics not good actual physics.